Log on, tune in, find out. Another good idea from Cambridge.
Something interesting.
Thank you very much. So what is something interesting? I'm going to talk about a classical problem. Laplacian u plus k squared qu equals 0. Helmholtz equation, and q is one constant or another, meaning q is q1 if the radius of x is smaller than epsilon, and q0 if the norm of x is greater than epsilon. Okay? And so you are given an incident wave. It's a scattering problem. So you're given an incident wave ui, which is a solution of the problem without a small bow. So Laplacian u plus k squared q0 ui equals 0, and ui is smooth. Okay? And so, okay, so you can decompose as you would. So let's put an epsilon because an epsilon is a problem. So you can say u epsilon is u incident plus u scattered, and u transmitted outside. This is for when x is greater than epsilon and when x is smaller than epsilon. And I mean R2 or R3. All right, and classical problem, q1 and q0 are two constants, and but what do I want to know? I want to know, I want to derive estimates for the scattered field for all q1 over q0 and all frequency. Okay. So this is not a new equation. It's
does it matter if q naught is bigger than q1?
no, it doesn't. It's any q1 over q0 between 0 and infinity, and any k between 0 and infinity. Okay, so this is a problem which could have been posed 100 and something years ago. There were even series developed to study this problem, and special functions to write solutions of that problem as a sum of series. And so you could ask, why is this question interesting now? You're polite, but you could wonder. And so let me give you a reason why I'm interested in that question. So I'm looking at, and I want to know that, of course, independently of epsilon. So looking at a small perturbation, a perturbation in a small area, so when you make a perturbation in a domain of a small radius, that's a problem which appears very often. So you could say there are two types of perturbation. There is a Born type of perturbation, meaning that you would say q1 is close to q0, or there are small volume perturbations. Small volume perturbation is saying, well, the measure on which q is not the background is small. Okay, and the small measure perturbation appears very often. So small measure of volume perturbation that appears in lots of places. And if you remember Joyce's talk last week, it appears when you do inverse problems, or when you do sensitivity analysis, or when you do hybrid methods and you want to find what is a small perturbation here and there. So to know what we know about small volume perturbation, let me start the first part of the talk will be a survey of what we know more or less on that problem on more difficult equations, but precisely. So let's start at frequency 0. So k equals 0. Okay, so if k equals 0 and I look at the Laplacian, there is not much perturbation there, but let's say I look at divergence of A epsilon grad U epsilon equals 0, and A epsilon dn U epsilon equals f. So this is in omega, on the omega, in a bounded domain. And you say A epsilon is A0 in omega except in a domain d epsilon, and A1 in d epsilon. Okay? And so if you say A1 is anything, so let's say A1 is in an infinity of omega, and A0 is smooth. What does smooth mean? It means that you need your solution to the solution of the problem without a perturbation to be smooth itself, to have some smoothness, to have, as we'll see. So what is the background problem? It's A0 grad U0 equals 0, and A0 dn U0 equals f. And you would like to know if this problem is a perturbation of this one. And so you could say you want to know the difference of U epsilon minus U0 on the omega, or simply an equivalent question is to say, can I compare the two energies? Say A epsilon grad U epsilon modulus of U epsilon squared minus A0 grad U0 squared. Do one energy converge to the other? Okay, so the result is that this is bounded by the volume of d epsilon times A1 minus A0 in an infinity of d epsilon times f in h minus 1/2 of the omega. Okay, and to have this, you just need, well, so what does the constant C depend upon? It depends upon A0 and A1. So I'm saying that A1 and A0 are two functions, but they are bounded between alpha and beta in 0 and infinity. And you just need the measure of d epsilon to tend to 0 as epsilon tends to 0. So there is no, you don't need any regularity on d. You just need this measure to tend to 0 for this expansion to hold. Okay. Meaning that, of course, this is true for d epsilon smaller than, say, 1/4, but okay, so this is actually.
So, can I interrupt you?
Yes?
So, you're saying epsilon has to go to 0, but the inequality doesn't have that. So you said, then I think you just said inequality holds when epsilon satisfies some bound.
D epsilon.
Is less than a quarter. I thought I heard you say that. Is that right?
Bounded by, well, if you want. Okay, so if you want bigger than 6, then you just increase your constant. But yes. Okay, you can see.
So
You can forget my comment if you want. You can say d epsilon greater than anything.
Okay,
But
C depends on epsilon somehow.
no, C is independent of epsilon. That's the point. C depends on A0, A1, so alpha and beta,
Okay.
and omega,
And then-
but and the regularity of A0.
And does it increase with omega?
Does it increase with omega? Well, it's your. It's. Does it increase with omega? No, it's no. It increases if omega becomes small. If you take a bigger omega, you're fine.
Okay.
Yes. No. All right. So your Okay, so this is, in this case, there are many things known. You know actually a representation formula for the difference. You know that in fact this is where polarization tensors appear, and you can characterize exactly the dependence in F in a much better way. You can represent U epsilon. Okay, that's not the subject of this talk, but this was something we looked at with Michael Vogelius in 2003. Now you could say, let's, what is important? Is a smooth background important? I said A0 has to be smooth, and the answer is so A0 smooth. Yes, that's important. And so consider the following problem. Say you're in a bowl, and your background is a constant A01 here, A02 here, and at the center of the bowl, I make a perturbation, which is my A1. Okay?
I just realized, I'm sorry, the question I asked was stupid because there's no frequency here, right?
No.
I apologize.
It's okay. A01, A02, and A1 is my perturbation in the center. Okay? And you want to know what is the difference between U0, the one without the perturbation, and the one with it. Well, in that case, instead there is something proportional to the volume. So let's say my ball here, this is a ball, the scaled ball of size 1, so epsilon B1. Okay? And so in this case, U epsilon minus U0 on the boundary, which is equivalent to looking at this difference of energy, is of the order of epsilon to the 2 lambda 1, where lambda 1 is a solution of a problem posed on a disk on the boundary between the 0 and the 1, and lambda 1 is strictly smaller than 1 and greater than 0 if A01 is not equal to A02. So smooth background is important to have a full volume size to appear. All right. Second question you can ask. So now a smooth background is assumed. So now, second question you can ask: what happens when the contrast becomes large? Well, see here I just said the measure of the epsilon goes to 0. So it could be anything. It could be, for example, a bunch of lines lying around periodically or not. I assume nothing, right? I just said measurable and goes to 0 with epsilon. So it could be a set of strings, but precisely in this kind of case, let's just consider a very thin inclusion, and let's make the coefficient go to infinity or 0. Well, you will get a crack, and the problem is that the limit problem is not the problem without the crack, and so there is no chance that you would get something in this case. So now, all right. So let's not. We can't be that general. We can't assume that. So let's say that now that my d epsilon is diametrically small, meaning that it is included in the ball epsilon b1. Okay. Then there is a result by Hoaimin Nguyen. I usually write only the last name, but in the case of Nguyen, it's important to write also the first name. And Vogelius from 2009, which shows that U epsilon minus U0 in any HS norm in omega without d epsilon is bounded by a constant which depends on S of times epsilon to the d, so your full measure, F to the h minus 1 half, and this constant does not depend on A1. So I can even take a sequence A1 of epsilon, and so that the fact that you have a small perturbation if you're diametrically small and it stays of the order of the volume is true independently of what contrast you put in. And this is true because there is a monotonicity principle for the zero frequency case. Okay, so now let's move on to Helmholtz and say, so there is a chance to show something in the zero frequency case contrast infinite, that's fine. You can get an estimate for the difference always. Okay, so now let's look at what happens when
But in this constant, the distance from the boundary as well?
yes, you want your inclusions to be, that's correct. You want your, well, in a mild way, meaning that you want your inclusion, yes, that's something I didn't say. You say your inclusion lives in a compact K, and your compact K, so d epsilon is somewhere in this, right, inside the ball, and this is at a fixed distance away from the boundary. You can't push it to, it's an internal problem. You say I stay at a fixed distance from the boundary, yes.
Do you have an idea how it happens if you go to the boundary?
You get, so for one ball, or in the general case where you could get funny things, because you could have Neumann-Dirichlet problems, and there are so high contrast, one ball on the boundary. I don't know the correct answer, but I suspect it's all right. It's just that, yeah, no, it should be okay. For one diametrically small case, I guess it would be fine. Yes?
Did you say A0 had to be smooth in this case? Is that the result?
Yes, absolutely.
How smooth is roughly?
So you want your background to be, you want U0 to be W1 infinity.
Okay.
And so that means, for example, C0, but C1 you're fine,
Yeah,
right?
okay.
Yeah. Okay, so Helmholtz. So we say I'm looking at the eventual A epsilon grad U epsilon plus K squared Q epsilon U epsilon equals 0, and A epsilon dm U epsilon equals F, and now on the omega, and you could say, can I do the same? And so you say I have A epsilon, which is A1 or A0. A1 is in infinity, A0 is smooth. This is in, and Q epsilon is Q1 or Q0. And you fix K. So the short answer is thing will work out the same way, provided that if K is not a resonant frequency of the unperturbed problem, so not the one with epsilon, but the unperturbed one. Okay, same type of results hold for finite contrast.
Sorry. I just maybe missed in your previous example. Probably everywhere it was assumed that mean value of f is equal to 0.
Yes, of course. Yes. The mean value of f is equal to 0 on the boundary of the omega, and well, and you have to, so in the if you don't have a q0, and or if you have a 0 eigenvalue, then you have to set that you set the value, the average of u epsilon, the average of u0 to be compatible. But yes. Okay, so there is a resonance question, but if you are away from resonances in the limit problem, you're all right. So the question of contrast is not so clear. It's not so clear in that case. And so just to do publicity, so to others, so there is a recent paper by somebody named Griesmeyer, who shows the same thing for the full Maxwell 3D, same hypothesis of a measurable limit and the same hold. So it's a, if you have a nice background, it's maybe it's not a Z, but that's 2010, I think. All right, so now that doesn't answer the question of what happens with the contrast and how the contrast plays with the frequency. Okay? So if you allow yourself to vary your contrast, so your contrast is not fixed, in particular it varies with epsilon, well, you run into a variety of problems, and you come into a regime which is close to the one that has been encountered by people doing cloaking by change of variable. And so for a fixed frequency, there is a paper of Greenleaf, Kurilev, Lassas, and Ullman. I'm quite sure you've heard of that paper before. And that's for, so there are two ways of doing cloaking by change of variable. Either you do it all the way through to make something disappear and show non-uniqueness, or you want to do approximate cloaking. Approximate cloaking. So approximate cloaking means that instead of really hiding you to zero, you say, I want my object to be cloaked. I'm not going to talk about cloaking in the rest, but I want my object to be cloaked, to be hidden in a small ball. Okay, and behind the cloaking by change of variable is a mapping to map a big ball of size 1 to a small ball of size epsilon. Okay, and so when you do that, there is a contrast which appears. All right, so does it work, this cloaking by change of variable, if you do an approximate cloaking approach? So there is a problem, which is that you could see some resonances. You could see it would seem that there are some frequencies where it's not seems, it proves that there are some frequencies where actually your cloak wouldn't work at all. Okay, and so if you just do a cloak which is not lossy, and so if you add the lossy layer, there is a paper by Kohn, Onofray, Vogelius, and Weinstein, which says that if you add a lossy layer and you shrink everything to a small ball, you'll be fine and you'll have a rate. It's not a great rate, it's 1 over log of rho when in 2D and rho when you're in 3D, but here's a rate. Now, what if you do a lossless, so this is lossy, and if you want to not add a lossy layer, but say I don't want to, and you fix the frequency, so in this case k fixed, and now k fixed again, lossless, the same Hoyman and Nguyen from before. I'm sorry, Nguyen, I pronounce it the French way. So this, I guess, is 2011 or 12. It's between a preprint and a published paper. Says that you can do a lossless cloaking by change of variable fine in 3D, that you have the same rate if you are outside of resonances, and the resonant frequencies come from the same or correspond to the same ones that Greenleaf Kurilev see, which is the Neumann eigenvalues of the internal problem inside your cloak. And if you are outside of resonances in 3D, it should work in the same way, and you can recover something. I mean, there is a trace which is something related to the eigenvector that you pick that has been left by your cloak to see through. So basically, you get nothing except this, some information about the eigenvector. Okay. So now back to my problem. There seems that you can do estimates, because all this is based on estimates for small balls. So you can do estimates, and I want to look at it in a simple case, and to see exactly what you can get, and if possible, get upper and lower estimates to see how far you go. So since I'm looking at a simpler problem, I also would like to know what happens when my frequency goes to 0, and this is relevant when you want to do numerical solvers for Helmholtz in 2 or 3D, and you want to, a good thing to check is to check that your solver is robust and allows you to go to small frequencies or high frequencies in a reasonable way. So there is such a solver being developed by Epstein and Charlie Epstein in Pennsylvania and Leslie Greengard in Courant. Okay, so now what did I say about U epsilon? U epsilon is my scattering solution. So U epsilon satisfies d over dr of U epsilon minus I omega square root of Q0 U U epsilon S equals little o of 1 over square root of r in 2D. I'll talk about the 3D in the end, but the 2D case is the more important one, let's say, and the more difficult one. Okay, so so we rescale the equation not to have too many parameters, and so you have actually 2 parameters which come into play. You have your contrast, after all you could divide everything, which is Q1 over Q0. That's my new variable. And you have your a-dimensional frequency, omega epsilon, which is square root of Q0, omega epsilon. Okay, so I have 2 parameters, and I want to get estimates. So even though I talked about cloaking and everything, you'll see things similar, but there is no more cloaking now. It's just this simple equation, 2 constants, and see what you get. So in which way am I going to... so those who came early have seen what is on the board below, but do not be afraid. This will not be a talk about Bessel functions. I will show you one of 2, but it will not be a talk about Bessel functions. So, so I'm in 2D, so let me draw a ball in 2D. I can do that. Centered in 0. And say I want to measure my scattered field on a sphere of radius r. Okay, so a function of 2 variables on the sphere of radius r becomes a function of 1 variable. It's even periodic, so it has Fourier coefficients. So I can calculate, so let me define the norm of f such that at x equals r, my h sigma norm is the square root of the sum of my Fourier coefficients at x equals r. And to make it a Sobolev looking, I put 1 plus modulus of n to 2 sigma. I put a square and a square root. Okay? So it's not very isotropic, but it's basically I am adding or removing regularity in the angular variable, and otherwise just Fourier coefficients of my function on the sphere. Right? So if I put a star, it means that I'm removing 0. And now, which means also that I am looking at f of x equals r minus the average on any ball, in particular the one I'm looking at of x equals r. Right, this is this. Okay. And so I said I want upper and lower bounds. So this is a bound which depends on r. So if I want something which is for all frequency and all contrast, I might want to even, as you see, the variable which appears is really this one, omega epsilon. So I might want to do something which doesn't depend on the specific r. So my curl n norm, star, say, of f is, do I put 2 pi's? Yes. Let me put 2 pi's for good measure. The square root of the sup over n not 0 Cn of f equals r squared, and that's a sum. Yes, sum. Cn of r 1 plus n to the 2 sigma. Okay, so I just take a soup over all radial directions. So that's just the infinity norm if you're thinking of radial function, right? And also, so this is to get something which is r independent, and to get I also need to compare another bound. So let's say not curl n of f, which is square root of 2 pi again, sup over n greater than p, sup over r greater than 0 of Cn of f x equals r 1 plus n sigma. Okay.
So let me guess, the soup in the first of the in lines, the soup is a soup over R positive.
R positive, thank you very much. Because the sum over sup r different from 0 is interesting, I agree. Okay, so the star norm h sigma is smaller than the curl norm in sigma. So is the np sigma, it's smaller than the curl norm. And if I have only one Fourier mode, well, I have the n norm sigma is also the n sigma p norm. Well, so one Fourier mode greater than p, and that's equal to the sup over r positive of the h star sigma norm. Okay. So they coincide in a certain way. All right. So let's start with perturbations. So I said I want to know something about perturbations. So first of all, what happens when around 0? So, and how far is around 0? Meaning, can I start from a 0 frequency or a very small epsilon? How far can I go? Okay, so suppose result 1, if you want, epsilon smaller than r, and my contrast smaller than 1. That's and now I have a first Bessel constant appearing, but don't worry, this is 0.89. Okay, so it's a constant, but it's a number. So let me write it. U epsilon s at x equals r h sigma is smaller than lambda 1 minus lambda omega epsilon factor of 9 omega epsilon ui 0, and 9 means 9, a number between 8 and 10. Omega epsilon r over epsilon. That's the absolute value. Plus 3 between 2 and 4. The norm of my incident field in the same HS norm with a bit less of regularity. With a bit more, less of regularity. Okay, so what does that mean? Well, it means that, so first of all, what is this? If you don't know Bessel functions, which I perfectly understand, I didn't either. So to two special functions, doesn't matter where they come from. Y0 is this one. It's a function which looks like a logarithm at 0 and which cuts the origin is y01, which is about 0.89. That's the number there. J0 is a function which corresponds to 1. And h10 is the square root of j0 squared and y0 squared. So around 0, y0 is like a log, h0 is like a log, and for a large number, it's like 1 over square root of x with a 2 pi in front of it. And disregard the other pictures. So what does this say? It says, well, this is completely a perturbative result. So here I have omega epsilon squared, which, if you think about it, is epsilon squared. Only there is the omega in it because, of course, the frequency will come in. And this is a square, just like we're in 2D, so this is the volume. You have 1 minus lambda, so that's your contrast, your Born approximation, if you want. This one, well, okay, so in fact, it's not really a square when you go to frequency 0. So if you make omega to go to 0 too fast, then you lose a little bit of frequency. You get omega squared log of omega, but that's okay. But in that other epsilon, you lose nothing. So this one, what is it? It's bigger than, so if I take an omega large enough, so larger than 0, this is just a number. And voila, and this is bigger than 1. So basically, if you say I take omega to be any number like 1/2 or something like this, well, this tells you that my scattered field is bounded. And you have explicit constants, 9 and 3. That's the advantage of Bessel functions. They have been studied for a long time with people who didn't have computers, so you have numbers. Omega epsilon is this. Square root of, it's the rescale frequency. So it's omega times epsilon. So this is, it's the high-dimensional frequency if you want. So that's the quantity which comes in.
But omega epsilon is out, there is an omega epsilon outside that whole square bracket.
And one inside.
So if omega goes to 0,
Yes.
doesn't that say that this norm is less than or equal to 0? Would that not conflict with...
Why would it be less than 0?
Well, I read the left side, it says the norm of u epsilon s,
Yes.
and then is less than or equal to something that is multiplied by omega epsilon.
Yes.
So even if epsilon is not 0, if I allow omega to be 0,
Yes.
I'm back to solving Helmholtz equation. And I
You
don't
mean
know
the
why you're saying
the impedance
scattered
equation.
field is 0.
Yes, because
The
there is
impedance
no
equation.
scattered field in the entire space. Just you have incident wave and it just goes through the space. There is no scattered field, right?
Why do I have Helmholtz
Lambda
equation?
is not
Wait.
1, epsilon is not 0.
Pause.
Why is it not a problem for Laplace's equation with a...
So my you're saying I have 0 of the term, so I have Laplacian u epsilon. That's what you're saying.
Yeah.
So k is omega. K equals omega.
That's an important equation.
Okay, but
But suppose k is 0, that's
yes,
what I'm asking.
yes. Well, what is the difference between my incident field and u epsilon? I'm looking at the scattered field, right? So the difference
Yes.
between there is no
And there's no scattered field
yes.
if I solve Laplace's equation with a spherical inhomogeneity.
There is no inhomogeneity anymore. It has
Isn't
disappeared
it? Where's it gone?
It's multiplied.
because it's multiplied by k.
Oh, because it's Laplacian, I apologise. Yes, I'm thinking it's that. I was thinking there was the A epsilon ratio.
No, it's in the 0 of the term.
Yes. I'm sorry.
That's right. Okay. Now, why? Now you could say, fine, but this is small frequency. So now I assume you know what my norms mean. So I'm going to erase them. This is small frequency. What happens if I want something for all frequencies? Still lambda smaller than 1. Well, lambda smaller than 1. I get that the sup over omega positive of my scattered field u epsilon s at x equal r h sigma is smaller than 5/2 square root of epsilon over r, my curled norm of my incident field, plus square root of 2 pi, my value at 0, x01, y01, r over epsilon. So it tells you it's bounded for any frequency. I mean lambda smaller than 1. Bounded for any frequency. It decays like epsilon over r, because if I take this one for r over epsilon, it goes like 1 over square root of x. And so your scattered field is under control for any frequency if your contrast is smaller than 1. Okay. Now you could say, why am I happy with those results?
That drops the constraint that omega epsilon is less than y01.
Yes, that's what so this is a perturbative result saying if omega epsilon is smaller than y01, this is where you get the omega squared or the epsilon squared. So the perturbation as in the equivalent of the zero frequency case, if you want. And this is for any frequency.
So omega epsilon is simply the diameter of the inclusion in wavelength,
Yes,
and it's just small.
almost. It's the diameter of the inclusion in the background wavelength.
Yeah, yeah. in the
Yes.
background.
Yes. Okay.
I'm missing it. Are you assuming omega epsilon
Here? No.
is that bound? No.
No. Here I'm saying for all omega.
Yeah.
So if this is just to say, how do you get the same result epsilon to the d for the Helmholtz case? Well, answer. You get this estimate. You could say so you get this estimate in terms of omega. So k times epsilon is your factor. So you could say, why do you think this is a good result? Why do you think it's optimal?
You have a y naught over there. I'm losing it here.
What is my y naught? Ah, this number.
Yeah,
So 0.89.
so you're still putting it in
Yes, it is here, but it's a constant factor,
there. Okay.
right?
All right.
H01 is a function. This is a constant factor. You can put 0.88, and the result is also true, or 0.5, 1/2, just number. And you have R epsilon, yes, because here there is no more frequency on the right, as you can see,
I see that.
as it should be because it's a soup. Okay. So why do I say this result is optimal? So at zero, so around the zero frequency, this is what you would obtain by a small perturbation calculation. Now, let's see. So this one. So now I look at the soup. I bound my frequency to be smaller than n0 and to be greater than 0. And I look at my scattered field. And notice that here my scattered field is fine. Here I'm not assuming my scattered field is fine up to my inclusion, right? And so if you want, this is a far field estimate, but the far field starts at the inclusion itself. Okay, it starts at epsilon. Things will be very different when lambda is greater than 1, but okay. So now I bound my frequency, and you get that at epsilon, my HS sigma star norm is greater than 1 over square root of 10, which is another number, about 0.3 maybe. My soup, my lower soup norm, and 0 of ui, meaning that this corresponds to the upper limit, if you want, of my frequency. So I look at epsilon, so I've removed my constant, and I've bounded my omega epsilon. I bounded below by a constant, and this is what I obtain. Okay, so the range is correct. And above that, there is no more decay. Okay, lambda greater than 1. Let's start with the good news. I'll say lambda greater than 1 and omega smaller than. So I agree that 0.89 is a confusing number. So now I'm going to use 1/2. Well, not really. I'm going to use 1/2 min of 1/2 and 1 over lambda square root of log of lambda plus 1. Then, for any epsilon smaller than r, I get the same thing, only here I have a 23. And here, of course, lambda minus 1. Yes. Okay. So same result, only now my range of application of the small frequency is much reduced because it depends on the contrast. I cannot go to frequency 1. Okay, but so I'll explain why this is true. But okay, so around 0 you have the same expansion with a different constant. Maybe 23 is too big. I do not guarantee that 3 and 23 are optimal, but they are numbers. And so if you want to try them in a code, if you get 24, you're wrong. Now, what is the equivalent of my all frequency estimate? The all frequency estimate now holds for lambda epsilon I don't know how much time I have because I don't have a watch. But
We can figure it out. You have 3 minutes.
really? Oh,
Well,
that's terrible.
that would be 55.
Okay, so I'll go over time. My sup, when my norm is greater than 0, now is bounded by the same constant as before, 5/2 cos lambda over r, my n norm of u, and plus square root of 10 pi instead of square root of 2 pi, u0, h10, and my max of 1/2 and my same constraint that here, lambda square root of ln of lambda plus 1, r over epsilon. Okay, so this is the far field starts at when lambda epsilon is smaller than r, meaning that it's not the background. What is important is that my the comparison of the wavelengths, the contrast or the inside wavelengths compared to the distance. Okay. You could say, so there is a gap, right? Because if this one tells me u is bounded for omega epsilon smaller than something, say more or less 1 over lambda, a bit more, but 1 over lambda. So if I don't have, by the way, if I don't have a 0 order term, I can just remove the logarithm. But if I have a 0 order term, the logarithm is necessary. So there is a gap because here I can do things for very small frequency, and here I have a gap. So what happens when omega is greater than 1 over lambda square root of ln of lambda plus 1, and epsilon is between r and lambda r. Okay. Well, in that case, you can get solutions like this one. So this is my incident field, ui, and this is my scattered field, us. So my incident field in this case is just one Bessel function. One Bessel function, which is J30 of square root of, say, q0 equal 1, so square root of omega r e to the 30 theta. That's my incident field. And my scattered field is is a scattered part. And so the scale here is that this is 0.2 and this is 5,100. 5,100, yes. Okay, so the far field starts here because my contrast is 2, lambda equal 2. So at the far field, you can see that my result is correct, meaning that the far field, both are comparable. The near field, at between epsilon and 2 epsilon, trouble. So this is the resonant problem. So I don't want to go too much over time. So I have to make a choice between what I talk about and what I don't talk about. Let's see. So, okay, so to make a long story short, this kind of thing shows that if you take, for example, a plane wave, e to the I omega x dot psi, your HS norm for any sigma will blow to infinity between epsilon and lambda epsilon. So your lower, that's the lower bound. The lower bound, if I take the soup over frequency, I can get it as large as I want. If I bound the frequency, I can get something which is geometric. So if I bound my frequency by, say, k, I can get something which is as large as k to the n, as the lower bound, meaning that I can find one frequency where this kind of solution will appear and will appear. So if I take the soup over all frequencies, well, I get plus infinity between 0 and lambda epsilon. Okay. But that's not, you could say, okay, well, fine, so there is no chance. There is, because those are quasi-resonances. So the same type of problem that they run into when cloaking by change of variable. But it's not completely true that they are everywhere. And so let me just write the final result for everything. Here it is. So now take any lambda positive and any epsilon smaller than 1 over 50. There exists I, depending on lambda and epsilon, such that I1 epsilon lambda is smaller than epsilon to the 1/8 log of epsilon. That's a set. And such that if I take the soup of square root of q0 omega in r plus without I1 of my HS norm, it is bounded by 21 square root of star 21 epsilon to the 1/4 over r, and my curl norm of ui. That's true for all r greater than epsilon to the 1/4. So there is no need to be in the far field. You can be in the reasonably near field. You cannot go up to epsilon, but you can go to a distance going to 0. And the set that you're removing is going to 0 with epsilon 2. Well, the size of the set. Yeah. And now your 0 order term, so this is a specific one in the 2D case, is that there is another set I0 such that you would get that the average of u is bounded by some, well, let's just say 2 over log of epsilon plus 1 to the 1/12 r, and this is I0, so set going to 0 but very slowly. And I apologize for going over time. So this means that the quasi-resonant frequencies basically disappear. I mean, are in a set of measure 0 when epsilon goes to 0. So you can, if you want to look at your inclusion and you're very unlucky, you will find one of them, but generically you won't see them. because you have uniform estimates.
How does the zeros of Bessel functions and their placement on the real line play a role here? Does it play a role?
Yes.
Yes, so you have some bound somehow. You said almost all of them are separated by some bound or something.
I don't. What do I need? So now you want to know about Bessel functions, eh? So
Well,
it's about.
when the zero is a Bessel function, that's interesting for me.
Yes. So it's about. The question is.
It's all the Bessel functions. I mean, you have a whole class. of
Yes.
Bessel. You have to look at all the zeros of that whole full class of Bessel functions.
Yes, of all Bessel functions. Well, all the regular Bessel functions.
Yes.
And so, where are your quasi-resonant frequencies? They are in every set. Okay, so they appear in every interval. Okay, so you're asking me where are the quasi-resonant frequencies? So, as we said, they are between. Let's say you get one Bessel function coming in, and then you have to sum them up. But after n, you're happy. After n, you're in the zone where your scattered field and your incident field, there is no difference between the singular solution and the non-singular solution. It's before n that things become complicated. Okay, so now you have, so here you have, so it's not really the Bessel, well, so it's a quotient of Bessel functions. So this is,
Zero, actually, it's where they're non-zero.
Sorry?
It's where they're non-zero, if you're looking before n.
Well, except that this is when this happens, of course, so lambda equal to 1. So this is between the zeros of the zeros of d over dx of jn of lambda x and the zeros of jn itself. So in each one of those intervals, so there are in each one of the intervals, there is exactly one quasi-resonant frequency. And so the question, so the worst ones are, of course, the lowest ones. So the one corresponding to n over lambda.
Okay, so for fixed n, I see, okay, good.
And then you sum it up. And what you want to do is to bound the side of your resonances, or your resonant phenomenon, away from those points. And so this is where the measure of those sets come in. That if you are reasonably away from those points, from those quasi-resonances, then you will be just like before. And what helps you is that this function becomes steeper and steeper as lambda goes to infinity.
Yeah.
And so the size of the set where quasi-resonances matter becomes smaller when the contrast increases. And so this is why you're able to derive a bound for any n and any lambda and everything.
Right, because it gets squeezed together, I guess. But I don't understand why all n doesn't play a role here. You just gave
It's
me
all
an
n, yes.
argument for one n.
Yes, and then you have to sum it up over all n.
All right, and you can do this.
Yes.
Okay, that's good, I'd like to see that. I like that very much.
Yeah. No, I'm not assuming that I have one incident wave. I'm saying this is for ui, which is a sum over any n in z of an, jn, so quote of q0 omega r e to the I n theta. This is your incident field because any smooth solution can be written this way, and then you can write those norms are perfectly adequate for this because those norms correspond basically to your ans times a constant times a jn. So you have to do something, but no, it's possible. No, there is a summing and there is some. I'm not showing you any Bessel function calculation, but there is a lot of Bessel function calculation. But that's, yeah.
And so it matters where these zeros are really close together somehow.
Yeah, but they are not too close. Well, so you have a lower bound on their distance, and between the derivative and themselves, because actually it become closer and closer. And but you're only looking in a certain range, right? You're looking between n and n over lambda.
That's what's saving it. That's
And
what's
so-
saving it, right?
But for a very, very big n if you want, but you can do something. Yeah.
Okay. Okay.
Yes?
You can interpret such kind of results in the following way.
Yes.
So epsilon is small, so you have small inclusion.
Yes.
So you kind of have two different problems, one for outer field, one for inner, in a stretch variable. So you can separate the scales.
Well, I'm not saying anything about the frequency, so
No, but say case, when for the case when say k is not too big, not too small, not extremely big. In a second, probably you'll see where I'm going. So
Okay.
for the inner problem, inner problem sometimes it can have its own eigenvalues.
yes, that's what they do in cloaking. Yes.
Yeah, and this is exactly eigenvalues of the inner problem which you are trying to
No.
avoid in your estimates.
No.
In the sense that this is exactly the situation when estimates are not so good.
It's a transmission problem, so it's not. Those are transmission eigenvalues. Precisely, it's not the same as. I understand that if you take epsilon to 0 exactly, as in the Curry-Lasswers case, you get Neumann on your boundary of the data. Although I should say the problem is really related to a change in U inside, but that's not so different. Okay, so to defend what I do, the analysis is actually about the same if you put A1, A0 inside. So
Is that right?
yes, because it's a decomposition in Bessel function, which is just, well, you add a new mu, but it
Yeah, 'cause it's
this resonance business is exactly the same. But then precisely if you're, this is where you get the Neumann part if you want. But here it's always a transmission problem. There is always a transmission.
Yes, the transmission problem. So by limiting problem, I mean the problem something
It's
like
not
this,
independent,
that
yes.
Laplacian of u outside of the ball of radius 1, and Laplacian of u is equal to lambda u.
Yes,
Yep. So it has its own eigenvalues.
outside.
Laplacian of u outside of ball.
Has no eigenvalue. Right, it's my,
No. Laplacian of u is equal to 0 outside of ball
yes.
of
Ah.
radius 1, and Laplacian of u is equal to lambda u inside the ball. This
But what do
one-
you put as a boundary value? What do you,
Just H2.
what do you mean H2?
Is boundary value mean interface conditions?
Yes.
Yeah, the function should just be in H2 space.
But precisely that's what doesn't work. You
This
see,
is
because
exactly what you have.
well, except that if you want to do things in, remember my picture. If you want to do things on with a high contrast, if you allow yourself to go to any frequency, you have a blow up all here. So no S will help you, right? You're in 0, you're H minus infinity if you want on the surface of your ball.
That's exactly what I'm trying to say. That this picture which you showed us,
Yes.
it looks like this is exactly the range of lambda when you have actually eigenvalue of inner problem.
Okay, so this is what, there is no mystery here. So omega is 17, epsilon is anything you want, and lambda equals 2. $17.41. I have more decimals if you want. But you have, if this is, what is 17.41? It's a number between the first zero of, it's a number between the first derivative of J0 30 and the first root, divided by 2.
May I also ask the question? In fact, for me, it seems that it's not so important that this Napier domain is sphere.
Yes, well, except that
any omega which
You did it with
is more or less the same.
I,
Only instead of eigenvalues of which corresponds to Bessel function, the eigenvalue of corresponding internal problem.
it's possible that you're correct.
He could, sorry.
Sorry. It's possible that you're correct. I have no idea how to prove it for a general domain. And so this is more of a, because you can do upper and lower bounds in this case, it's more of a benchmark if you want to prove something in a more general domain, because you can do better. I don't think you can do much better than those lower and upper estimates because they are lower and upper estimates. And so you might be able to change the constant, but that's about it. And so,
In Russia, the such kind of investigations, this type of, I
Yes.
say, provided by two scientists. It's one of them is Nazarov,
Yes.
and the second one is Ilyin. Both of them more or less deal with arbitrary domain, which shrinks.
Yes. That's a sensitivity analysis, but I completely agree. This is for optimization, but it doesn't. This works. For what I saw of this work, and I think I'm not too far from knowing what they do. Is that this is for bounded frequencies, and so if you fix k, if you bound the frequency, and you take epsilon go to 0, you can do all sorts of things. But here I'm not saying I allow the frequency to move with epsilon. You see those sets depend on epsilon and lambda very strongly. So I say, give me any frequency. I want to know what happens when epsilon goes to 0, but I don't want to impose the frequency. I want to
So you try
estimate.
to obtain results in all
Uniform,
these,
yes. And so there is not a uniform result without removing a set picture, but there are some with a set going to 0.
But
That's
for this guy, it don't matter what kind of domain.
I know, yes, because you do it by comparison, yes. But that's a bounded frequency.
You could,
Well, it matters what kind of domain, because as I said, if you take a stretched domain, you'll have a problem. You have to take a domain which is diametrically bounded, and then you get those uniform estimates. I agree. But if you take a domain which is stretched, then you can get a crack, and which means that when the contrast becomes large, and then the boundary problem is not the same as the problem without the crack.
how important is it to really know what the series solution looks like? Because it seems to me, at least at a high level, at which I could hear what you were saying,
Yes.
is that you need some kind of this bound about this interval, and if you made an assumption about that, would that be enough or do you actually need the series representation? Do you actually use?
Well, so you want the low frequency estimate to go as far as you can, and this is helpful to know what to do. Okay. The second thing is that you want also to know that your reflection won't blow up if you're away from those points. And for this, you have to basically have some handle on what you're doing. But it's possible that, yes, with the correct hypothesis saying that if you're away from those points, yes. So if you could reword it in a different way and say, if I put myself away from those sets, I am okay. But then, if you say that, then you'll have a set of size 1. Because or even infinite size, right? You would have something which is not going to 0 with the measure. So you have to say, and my set in which I have things are okay, are decreasing when my frequency goes up, and around that. So more or less you're saying, well, so you're saying too much, a little bit too much. I mean, that's a lot of things to prove, which is perfectly fine if you can prove them. But as an if theorem, it's a long if.
I see now what you're telling, that you not only have to have this bound on these little intervals, but you also have to sum them up.
Yeah.
So this is a big assumption.
So this is in asymptotic analysis to appear maybe in a month or something.
Okay. Let me know.
Thank you. Those who survived, so I'm sorry to go.